You know, in an organic molecular rearrangement reaction, an atom or group moves from one atom to another in the same molecule. That is, connectivity of atoms changed within the molecule. That is, an atom or group moves from one atom to another within the same molecule. That is what is called the molecular rearrangement. That means the connectivity of atoms changed within the molecule. Most of the migrations are from an atom to an adjacent one. That is called one-to shift. But some are over longer distance. Most of them are one-to migrations. The migrating groups may migrate with an electron pair, and such rearrangement is called nucleophilic rearrangement, or without electron pair, or electrophilic rearrangement, or with one electron, that is free radical rearrangement, as the case may be. The rearrangement reactions can be roughly classified on the basis of migration origin and migration terminus as rearrangement to electron deficient carbon atom, rearrangement to electron deficient nitrogen atom, rearrangement to electron deficient oxygen, sigmatropic rearrangement, and other rearrangement. These are the important classification of organic molecular rearrangement reaction. Among the rearrangements to electron deficient carbon atom, the important reactions or rearrangements are Wagner-Meerwein rearrangement, pinacol-pinacolone rearrangement, Demjanov rearrangement, benzyl-benzylic acid rearrangement, Wolff rearrangement, diene on phenol rearrangement. All these rearrangements are involving rearrangements to electron deficient carbon atom. Okay, in this video, I will be discussing Wagner-Meerwein rearrangement, which involves the migration of atom or groups to the electron deficient carbon atom. Wagner rearrangement is one of the simplest system of rearrangement where an alkyl group migrates with its bonding pair to an electron deficient carbon atom. For example, if you treat an alcohol with an acid, an alkene is obtained with a rearrangement involving the migration of alkyl group from one carbon atom to another, a one-to shift. The mechanism of reaction can be represented like this. Here, acid donates proton to this OH group to form the protonated alcohol, which eliminates a molecule of water, forming this carbocation. Here, this carbocation, it is secondary carbocation. Thus, an alkyl group from the next carbon atom migrates to this carbocation. Thereby, a new carbocation which is tertiary is formed. See, this carbocation, it is tertiary carbocation. It is secondary carbocation while it is tertiary carbocation. Then a proton is eliminated, thereby an electron pair shift between these two carbon atoms, forming a double bond. Thereby this alkene is formed. It is the mechanism involving Wagner-Meerwein rearrangement. Okay, Wagner-Meerwein rearrangements are usually common in bicyclic system. For example, you can see the conversion of isoborneol to camphene involves Wagner-Meerwein rearrangements. For example, isoborneol on treating with acid, as we explained, it absorbs or proton is captured by this OH group and water is eliminated to form this carbocation. It is secondary carbocation. Thereby 1,2 alkyl shift takes place. This alkyl group shifts from this carbon atom to this carbon atom, and so 1,2 shift, 1,2 alkyl shift takes place to form this tertiary carbocation. This tertiary carbocation, and from this tertiary carbocation, a proton is eliminated from this CH3 group, thereby forming this alkene, which is called camphene. That is how camphene is produced from isoborneol through Wagner-Meerwein rearrangement. Okay, then another example. Here, this bicyclic compound, as in the previous case, protonation takes place into this alcoholic group. Thereby, protonated alcohol is formed, eliminated a molecule of water, forming this secondary carbocation. Methyl shift 1 to alkyl shift takes place from this carbon atom to this carbon atom. Thereby, this carbon atom becomes positively charged the carbocation, or a tertiary carbocation is thereby formed, and proton is eliminated from this carbon atom. Thereby, a new double bond is formed between these two carbon atoms. Thereby, this alkene is formed. It is another important example of Wagner-Meerwein rearrangement in bicyclic system. Another important example is this. Here, this alcohol, on treating with the acid, protonation takes place as in the previous case, as we discussed in the previous case. Protonated alcohol is formed. It eliminates a molecule of water, forming this carbocation. It is a secondary carbocation. Then methyl shift from this position, 4,5 position, this alkyl shift takes place from this fifth carbon atom to this sixth carbon atom. Thereby 1 2 alkyl shift takes place here, thereby forming this carbocation. And again, see, it is a tertiary carbocation. And from this tertiary carbocation, a proton is eliminated from this methyl group, or from the eighth carbon atom. It is the methyl group, and a proton is eliminated from here, forming this alkene. Okay, all these reactions involving Wagner-Meerwein rearrangement reaction. So we can say this rearrangement, Wagner-Meerwein rearrangement, is commonly seen in bicyclic system. See, Wagner-Meerwein rearrangement is usually involving carbocation shifts. This carbocation may be produced by varieties of ways, not only from the alcohol. Carbocation may be produced from halo compounds. For example, this halo compound, on heating, eliminates this halogen, forming this carbocation. And this carbocation, from this carbocation, uh, an alkyl group shift from this adjacent position to this position. Thereby, 1 2 shift of alkyl group takes place to form this new carbocation. From this new carbocation, as in the previous case, a proton is eliminated, forming a double bond between these two carbon atoms. Thereby, this alkene is formed. And it is also a molecular rearrangement called Wagner-Meerwein rearrangement. Usually, less stable cyclic carbocation converted into a more stable one through an expansion or contraction reaction. For example, this reaction involving a contraction of ring, this carbocation gets converted into this carbocation, where ring contraction takes place through the alkyl shift from one position to the adjacent position, or 1 2 alkyl shift. This rearrangement also involving 1 2 alkyl shift, whereby contraction of ring takes place. It is also a Wagner-Meerwein rearrangement. You know, aryl groups usually have a greater migratory aptitude than alkyl group or hydrogen due to the formation of lower energy bridged phenonium ion, and hence a molecule involving aryl group is highly susceptible for 1 2 shift. Thereby, such compounds also give Wagner-Meerwein rearrangement. See this example. It is a halide which containing an aryl group here. See, this on treating with an acid. First of all, halogen gets eliminated, forming a carbocation, whereby it is a actually a primary carbocation. It is highly unstable. Thereby, this bond gets shifted here to form this phenonium ion. It is a bridged phenonium ion. This phenonium ion is stabilized via resonance. And this phenonium ion, and from this phenonium ion, this aryl group shifted from this position to this position, or 1-2 shift takes place, or aryl group from here migrates to this carbon atom, or a 1-2 shift takes place, thereby forming this carbocation, a tertiary carbocation. From this tertiary carbocation, a proton is eliminated from this carbon atom, thereby a new double bond is formed between these two carbon atoms, forming this molecule. It is also an example of Wagner-Meerwein rearrangement involving aryl group migration. Another important example of Wagner-Meerwein rearrangement is conversion of camphinylol to xanthine, camphinylol to xanthine, which involves Wagner-Meerwein rearrangement. For example, camphinylol, on treating with the acid, protonation takes place to form this protonated alcohol. It eliminates a molecule of water, forming this carbocation, a tertiary carbocation. And this, from this tertiary carbocation, a proton is eliminated, forming this xanthine. Okay, that is, first of all, protonation takes place, forming protonated alcohol, elimination, followed by migration of this alkyl group from this position to this position, or 1-2 alkyl shift takes place, forming a more stable carbocation, and elimination of proton, leading to the formation of the product xanthine. Okay, usually the direction of rearrangement is to form a more stable carbocation, that is tertiary. If there is a chance for formation of tertiary carbocation, it will form predominantly than secondary, and the secondary is formed more predominantly than primary carbocation. Okay, so I have already discussed Wagner-Meerwein rearrangement with many examples, and also discuss the mechanism involving each of these examples. I think you might have understood all these aspects of Wagner-Meerwein rearrangement and its mechanism. So I hereby conclude this video. Thank you for watching. Thank you.